Most terrifying theories of the universe. Imagine for a moment that everything you know, everything you've ever loved, every memory stored in your brain, every star in the night sky, every galaxy spinning in the cosmic void, could disappear in an instant. Not in some distant, abstract future, but potentially right now, as you listen to these words. There's a wave moving through space at the speed of light, invisible, unstoppable, and absolutely destructive. You wouldn't see it coming. You couldn't prepare. One moment you exist, and the next, you and everything around you would simply cease to be, torn apart at the most fundamental level of reality itself. This isn't science fiction. This is a genuine possibility that keeps cosmologists awake at night, one of many terrifying theories about the universe we inhabit. Close your eyes and picture the universe as you understand it. Vast, ancient, filled with billions of galaxies, each containing billions of stars. Beautiful, isn't it? Now ask yourself this question. What if everything you think you know about reality is wrong? What if the universe isn't the stable, predictable place we've assumed it to be, but rather a cosmic ticking time bomb with multiple ways to end not just humanity, not just Earth, but existence itself as we know it? The uncomfortable truth that scientists have discovered over the past century is that our universe is far stranger and far more terrifying than our ancestors could have ever imagined. The monsters aren't hiding under your bed or lurking in dark forests. The real monsters are woven into the very fabric of space-time itself, and they operate on scales so vast and mechanisms so bizarre that they challenge everything we think we understand about reality. Let me take you on a journey through the most disturbing theories that modern physics and cosmology have produced. These aren't the ravings of conspiracy theorists or the plots of horror movies. These are serious scientific hypotheses proposed by some of the brightest minds in physics, backed by mathematics and observational evidence, published in peer-reviewed journals and debated at the highest levels of academic discourse. They represent our best attempts to understand the universe we live in, and what they reveal is nothing short of terrifying. We'll start with something that sounds almost poetic in its horror: the heat death of the universe, also known as the Big Freeze. This theory emerges from one of the most fundamental laws of physics, the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases over time. Always. Without exception. This law is so ironclad that physicist Arthur Eddington once said that if your theory is found to be against the second law of thermodynamics, there is nothing for it but to collapse in deepest humiliation. Think about an ice cube melting in a glass of water. The organized structure of ice breaks down into the more disordered state of liquid. Heat flows from hot to cold, never the reverse, without external energy input. This seems trivial in everyday life, but when you apply this principle to the entire universe, something chilling emerges. The universe, according to our best measurements, is like that ice cube, slowly but inevitably moving toward a state of maximum entropy, maximum disorder, where no energy can flow because everything has reached the same temperature. Picture this: trillions upon trillions of years in the future, long after our sun has died, long after every star in every galaxy has exhausted its fuel and winked out of existence. The universe has expanded so much that galaxies are separated by distances so vast that light from one will never reach another. The cosmic microwave background radiation, the afterglow of the Big Bang that currently bathes the universe at about 3 degrees above absolute zero, has cooled even further, approaching absolute zero itself. In this future universe, there are no stars. There is no light. The last stellar remnants, white dwarfs and neutron stars, have radiated away their final heat. Even black holes, those gravitational monsters that devour everything, have evaporated through a process called Hawking radiation, a quantum mechanical effect discovered by Stephen Hawking that shows even black holes aren't eternal. The largest black holes might take 10 to the power of 100 years to evaporate, a number so large it's almost meaningless to human comprehension. For comparison, the current age of the universe is merely 13.8 billion years, less than 10 to the power of 11 years. What remains in this final state? A cold, dark, empty void filled with nothing but a thin soup of photons and fundamental particles, spread so far apart that they might never interact with another particle again for eternity. No structures, no complexity, no life, no thought, no possibility of anything happening at all. This is heat death, a universe in perfect equilibrium, where entropy has reached its maximum, and therefore nothing can ever change again. Time, in any meaningful sense, has ended. Ask yourself, if the universe is destined to end in this way, does anything we do matter? Does meaning exist in a cosmos that is fundamentally doomed to eternal, frozen emptiness? But wait, because it gets worse. Some cosmologists believe the universe won't die in ice, but in something far more violent and strange. This is called the Big Rip, and it's based on observations about dark energy, that mysterious force that makes up roughly 68% of the universe and causes space itself to expand at an accelerating rate. In the late 1990s, two teams of astronomers studying distant supernovae made a shocking discovery that would earn them the Nobel Prize. They expected to find that the universe's expansion was slowing down due to gravity, like a ball thrown into the air that eventually falls back down. Instead, they found the exact opposite. The universe's expansion is speeding up. Something is pushing space apart, working against gravity, and we have no idea what it is. We call it dark energy because we're in the dark about its nature. Here's where it becomes terrifying. Most cosmological models assume that dark energy has a constant density throughout space and time. But what if it doesn't? What if dark energy gets stronger over time? This possibility leads to the Big Rip scenario, and it's exactly as violent as it sounds. Imagine dark energy becoming more powerful, pushing space apart with ever-increasing force. Currently, dark energy is weak enough that it only affects the largest scales of the universe, pushing galaxy clusters apart. Gravity holds galaxies themselves together, keeps stars in orbit, keeps planets around their suns, keeps atoms intact. But if dark energy grows stronger, it eventually overcomes gravity at smaller and smaller scales. First, galaxy clusters are torn apart. Then individual galaxies. Then, as dark energy continues to intensify, solar systems are ripped to pieces, planets torn from their orbits and sent careening into the void. But it doesn't stop there. As dark energy becomes more powerful still, it overcomes the electromagnetic forces holding molecules together. The Earth itself, if it still existed, would be shredded into its component atoms. Then, in the final moments, even atoms are torn apart, electrons ripped from nuclei. Even atomic nuclei themselves, bound by the strongest force in nature, the strong nuclear force, are pulled to pieces. And all of this, according to some models, could happen remarkably quickly. Once the Big Rip begins in earnest, the final destruction from galaxy shredding to atom ripping might take only a few months. The last moments would be the most horrifying. Every particle with structure being torn apart in what physicist Robert Caldwell and colleagues called the cosmic doomsday. The good news, if you can call it that, is that most evidence suggests dark energy is probably constant, making the Big Rip less likely than heat death. But we don't know for certain. We can't know for certain. Dark energy remains one of the deepest mysteries in physics, and until we understand what it actually is, we can't completely rule out that the universe might tear itself apart. Now, let me introduce you to something even stranger, a theory so disturbing in its implications that when it was first proposed, some physicists thought it was too unsettling to be taken seriously. This is the false vacuum theory, also known as vacuum decay or vacuum metastability, and it suggests that the universe itself might be fundamentally unstable, existing in a precarious state that could collapse at any moment. To understand this, you need to think about what physicists mean by vacuum. In quantum field theory, the vacuum isn't empty nothingness. It's the lowest energy state of all the quantum fields that permeate space. Think of it like a valley in a landscape of hills. A ball placed in the valley will stay there because it's at the lowest point. This is called a true vacuum, the absolute lowest energy state possible. But what if our vacuum isn't actually in the lowest valley? What if we're in what looks like a valley, But there's actually a deeper valley somewhere else in the landscape, separated from us by a hill. This would be a false vacuum, a metastable state that seems stable but actually isn't. The ball could sit in this false valley for a very long time, but if it gets just enough energy to roll over the hill, it will fall into the true, deeper valley. Now scale this up to the entire universe. If our universe exists in a false vacuum state, then the quantum fields that make up reality could suddenly transition to the true vacuum state through a process called quantum tunneling. This could happen anywhere, at any time, completely randomly, with no warning whatsoever. When it happens, a bubble of true vacuum appears, expanding at the speed of light in all directions. Inside this bubble, the laws of physics are different. The fundamental constants that govern reality, things like the mass of electrons or the strength of fundamental forces, would have different values. Atoms as we know them couldn't exist. Matter would tear apart or reorganize into forms completely alien to our universe. The wall of this bubble, the boundary between true vacuum and false vacuum, would be a roiling hell of pure energy, more intense than the core of any star. As it expands at light speed, you would never see it coming. You couldn't, by definition, because information can't travel faster than light. The first and only indication that vacuum decay had begun would be the moment of your destruction, as the bubble wall overtook your position and every atom in your body was subjected to different physical laws. Behind the bubble wall, in the new true vacuum, the universe would be unrecognizable. Stars couldn't form. Life as we know it would be impossible. Everything that makes our universe habitable and stable would simply cease to function. And here's the truly terrifying part. This could happen right now. It could have already happened somewhere in the universe, with a bubble of true vacuum expanding toward us at light speed, devouring galaxies as it grows, and we would have absolutely no way of knowing until the instant it arrived. Ask yourself this. How do you make peace with the fact that existence itself might be fundamentally unstable, that reality could end without warning at any moment? In 2012, when physicists at CERN discovered the Higgs boson, there was celebration around the world. This particle, responsible for giving other particles mass, was the last missing piece of the standard model of particle physics. But the celebration was tinged with concern, because the mass of the Higgs boson, measured at about 125 billion electron volts, places our universe very close to the boundary between stability and instability. Physicists calculated that with this Higgs mass and the measured mass of the top quark, our universe appears to be in a metastable state. Not definitely unstable, but not definitely stable either. We're in that false vacuum, sitting in what might not be the deepest valley. The calculations suggest our vacuum should be stable for an extraordinarily long time, much longer than the current age of the universe. But extraordinarily long isn't the same as forever. Stephen Hawking, in one of his last papers before his death, pointed out that the metastability of our vacuum was concerning. He noted that we don't fully understand all the physics involved, and there could be factors we're missing that might make our vacuum more stable or less. We simply don't know. Some theorists have proposed that high-energy events, like particle collisions at particle accelerators or even incredibly energetic cosmic events, might trigger vacuum decay. This sparked brief controversy when the Large Hadron Collider was being built, with some people worrying that colliding particles at such high energies might create the quantum tunneling event that would start the cascade. Physicists were quick to point out that cosmic rays bombard Earth with far higher energies all the time, and have been doing so for billions of years without triggering vacuum decay, so clearly the collider was safe. But that raises an interesting question. Why hasn't vacuum decay happened already? The universe is 13.8 billion years old and vast beyond human comprehension. If vacuum decay is possible, why hasn't some random quantum fluctuation somewhere in all that space and time already triggered it? There are several possible answers. Maybe vacuum decay is so incredibly unlikely that even given billions of years and billions of light years, it simply hasn't happened yet. Maybe our vacuum is actually completely stable, and we're just uncertain about it because our physics is incomplete. Or maybe, and this is a disturbing thought, vacuum decay has happened, and there's a bubble expanding somewhere in the universe right now, but it's so far away that it hasn't reached us yet. Given the expansion of the universe, it might never reach us, or it might arrive in the distant future. Or perhaps we're protected by the anthropic principle. We exist in this particular patch of the universe precisely because it hasn't undergone vacuum decay. Any regions where it did happen are now sterile voids where no observers exist to ask questions about vacuum stability. We're here because we're in a place that hasn't been destroyed yet. Let's shift gears to something that might make you question the very nature of your existence. The simulation hypothesis. This theory proposes that our universe, with all its complexity and vastness, isn't the base level of reality but rather a sophisticated computer simulation created by some advanced civilization. The modern version of this idea was popularized by philosopher Nick Bostrom in 2003, though the concept has roots going back further. Bostrom's argument is based on probability and assumes that civilizations can eventually create simulated realities so sophisticated that conscious beings within the simulation don't realize they're simulated. If this is possible, Bostrom argues, then at least one of three things must be true. First, civilizations almost never reach the technological level needed to create such simulations. Second, civilizations that reach this level choose not to run such simulations, perhaps for ethical reasons. Or third, we are almost certainly living in a simulation. The logic goes like this. If creating ancestor simulations is possible and civilizations choose to do it, then there would be vastly more simulated realities than base reality. There's only one real universe, but potentially millions or billions of simulated ones. Therefore, by pure probability, if you find yourself in a universe, it's more likely to be simulated than real. Think about how video games have evolved. In just a few decades, we've gone from simple pixels on a screen to photorealistic virtual worlds. Games now feature complex physics engines, artificial intelligence, vast open worlds with weather systems and ecosystems. Now project that technological development forward not decades but millennia or millions of years. What might be possible? A sufficiently advanced civilization might have computing power that would seem magical to us. They might be able to simulate entire universes, with billions of galaxies, each containing billions of stars, with all the quantum mechanical complexity that entails. To the simulated beings within that universe, everything would seem completely real because their consciousness itself would be part of the simulation. Are you certain you're not in a simulation right now? Ask yourself, what evidence could you point to that would definitively prove you're in base reality and not a very sophisticated simulation? Some physicists have proposed ways we might detect if we're in a simulation. For instance, if the universe is being simulated on a grid-like computational structure, we might find evidence of this grid at the smallest scales, where space-time itself might show pixelation or quantization beyond what quantum mechanics predicts. Some researchers have suggested looking for glitches or artifacts in the cosmic microwave background radiation, like a programmed reality showing errors. Elon Musk has famously stated that he believes there's only a 1 in billions chance that we're in base reality. His reasoning echoes Bostrom's argument. Given how quickly computer technology is advancing, it seems almost certain that we'll eventually be able to create realistic simulations, and if we can, we probably will, and if we will, others already have. But this theory opens up deeply unsettling questions. If we're in a simulation, who created it? What is their purpose? Are we an experiment, entertainment, or perhaps an ancestor simulation created by our own descendants to study their history? Could the simulation be turned off at any moment, ending our universe as easily as closing a program? Even more disturbing, what are the ethical implications? If we're simulated, do we have free will, or are our choices programmed? Is suffering in a simulation less real than suffering in base reality? If future humans create simulations with conscious beings, are they responsible for all the suffering within those simulations? Some philosophers argue that the simulation hypothesis is essentially unfalsifiable, meaning we can't prove it wrong, which makes it more of a philosophical proposition than a scientific theory. Others point out that even if we are in a simulation, physics still works the same way from our perspective, so it doesn't change how we should do science or live our lives. But there's something deeply terrifying about the possibility that everything you experience, every person you love, every achievement and struggle, exists only as information in some incomprehensible computer, running at the whim of beings whose motives you can't know and whose existence you can't prove. Now let me introduce you to one of the most mind-bending concepts in cosmology: Boltzmann brains. This thought experiment reveals a deep paradox in our understanding of the universe and leads to conclusions so bizarre that they seem like madness. The concept is named after Ludwig Boltzmann, a 19th-century physicist who worked on statistical mechanics and entropy. Here's the basic idea. In a universe that exists for an infinite or extremely long time, random quantum fluctuations could spontaneously create complex structures, including brains complete with false memories. Remember our discussion of heat death, where the universe eventually becomes a nearly empty void with occasional particles spread vast distances apart. Even in such a universe, quantum mechanics allows for random fluctuations. Given enough time, truly vast amounts of time, these fluctuations could randomly assemble into structures. Most fluctuations would be tiny and simple, but very rarely, by pure chance, a complex structure could form. Here's where it gets weird. It's far more probable for a fluctuation to create a single disembodied brain, complete with memories and sensory inputs, than to create an entire universe like the one we observe. A brain on its own requires much less ordered structure than an entire observable universe with billions of galaxies. This leads to a disturbing possibility. If the universe will exist for an extremely long time or forever, then most observers in the history of the universe wouldn't be creatures who evolved naturally on planets, but rather these Boltzmann brains, randomly fluctuated into existence with completely false memories of lives they never lived and observations of universes that don't exist around them. And here's the truly unsettling question. How do you know you're not a Boltzmann brain right now? You have memories of a childhood, relationships, experiences, but so would a Boltzmann brain that spontaneously formed just 1 second ago in the cosmic void, complete with false memories of reading the script. Your entire life could be an illusion, a random fluctuation destined to dissolve back into chaos in the next moment. Cosmologists actually take this problem seriously because it threatens the validity of scientific reasoning itself. Science is based on the assumption that our observations of the universe are generally reliable. But if Boltzmann brains are more common than naturally evolved observers, then our observations are probably unreliable, being random hallucinations rather than accurate perceptions of reality. This is called the Boltzmann brain problem, and it's forced cosmologists to carefully consider which models of the universe are viable. A cosmological model that predicts Boltzmann brains will outnumber regular observers is generally considered problematic and rejected on anthropic grounds. We assume we're not Boltzmann brains, and therefore we favor models of the universe where naturally evolved observers are more common than spontaneously fluctuated ones. But notice what we're doing here. We're rejecting certain models of the universe not because they're inconsistent with data, but because they lead to philosophical conclusions we find unacceptable. This is controversial among physicists. Are we letting our preferences dictate which theories we accept? Or are we using legitimate logical reasoning based on the anthropic principle? The Boltzmann brain paradox highlights something deeply strange about probability, infinity, and existence. It shows that our intuitions about reality can lead us astray when dealing with concepts like infinite time or infinitely large multiverses. Let's turn now to a theory that has profound implications for humanity's future: the Great Filter. This isn't about the universe ending, but about why the universe seems so empty of intelligent life, and what that might mean for our survival. The Fermi paradox, named after physicist Enrico Fermi, poses a simple question: where is everybody? The universe is vast and ancient. Our galaxy alone contains hundreds of billions of stars, many with planets. Many of those planets are in the habitable zone where liquid water can exist. Some of those planets are billions of years older than Earth. If life and intelligence are natural outcomes of the right conditions, the galaxy should be teeming with civilizations. Some should be millions or billions of years more advanced than us. They should be everywhere, colonizing the galaxy, leaving obvious signs of their presence. Yet we see nothing. We hear only silence. The Great Filter is a proposed solution to this paradox, introduced by economist Robin Hanson in 1996. The idea is that somewhere between the emergence of life and a civilization becoming capable of colonizing the galaxy, there's an extremely difficult step, a filter that almost no species passes through. This filter would explain why we don't see alien civilizations. Most don't make it past the filter. Here's the terrifying part. We don't know where the Great Filter is. There are two broad possibilities, and one is far more disturbing than the other. Possibility 1. The Great Filter is behind us. Perhaps the emergence of life itself is incredibly rare, or the jump from single-celled to multi-celled organisms, or the evolution of intelligence. If the filter is behind us, then we're exceptionally lucky to exist, but our future is bright. We've passed the hardest step. Possibility 2. The Great Filter is ahead of us. This is the nightmare scenario. This means that civilizations regularly reach our level of development, but then almost always fail to advance much further. Something kills them off or prevents them from expanding into space. What could this filter be? Nuclear war? Environmental collapse? Artificial intelligence that destroys its creators? A fundamental limit to space travel that we haven't discovered yet? Some cosmic threat we're not yet aware of? The possibilities are endless, and almost all of them are existential threats. When we search for life in the universe, ask yourself this: should we hope to find it, or should we hope we don't? If we discover evidence of extinct alien civilizations, civilizations that rose and fell without reaching the stars, it would strongly suggest the Great Filter is ahead of us, and our chances of survival are slim. The silence of the universe might actually be good news, suggesting the filter is behind us, in our past. But there's an even darker possibility some researchers have proposed. Perhaps the Great Filter isn't a single obstacle but multiple filters, and we've only passed some of them. Maybe life is rare, intelligence is rare, and technological civilizations almost always destroy themselves. We could be facing multiple catastrophic threats in our future. Astronomer and science communicator Carl Sagan spoke about this in the context of nuclear weapons. He pointed out that the same scientific knowledge that allows us to reach the stars also gives us the power to destroy ourselves. He wondered if perhaps every civilization reaches a point where they gain tremendous destructive power, and most fail to mature enough to handle it responsibly. Think about humanity right now. We have nuclear weapons capable of rendering Earth uninhabitable. We're changing our climate in ways that could trigger cascading catastrophes. We're developing artificial intelligence without fully understanding how to control it. We're editing genes, creating synthetic organisms, exploring nanotechnology, and accumulating knowledge that could be weaponized in terrifying ways. We're also becoming more interconnected, meaning a single catastrophe could potentially affect the entire globe. Are we approaching a Great Filter right now, in our lifetime? Is the silence of the stars a warning? Some optimistic thinkers argue that the Great Filter might not exist at all, that the Fermi paradox has other solutions. Maybe intelligent life is common, but interstellar travel is so difficult that civilizations stay confined to their home systems, invisible to us at these vast distances. Maybe aliens are out there but choose not to communicate. Maybe they're so different from us that we don't recognize their signals. Maybe they're already here, observing us, but staying hidden. But the Great Filter remains a compelling explanation, and the implications are sobering. If it's ahead of us, then humanity's next few centuries might be the most critical period in our entire future. We might succeed in passing the filter and go on to spread among the stars, or we might join the countless other civilizations that the universe has presumably watched rise and fall into extinction. Let me now take you into the realm of quantum mechanics, where reality becomes stranger than fiction, and where some interpretations lead to truly disturbing conclusions about the nature of existence. I want to talk about quantum immortality, a thought experiment that emerges from the many worlds interpretation of quantum mechanics. First, understand that quantum mechanics, the physics of the very small, is weird. Particles can be in multiple states simultaneously until observed. Measurements affect outcomes in ways that seem to violate our intuitions about cause and effect. The theory works spectacularly well at predicting experimental results, but what it means for the nature of reality is hotly debated. One interpretation, proposed by Hugh Everett in 1957, is the many worlds interpretation. It suggests that every time a quantum event has multiple possible outcomes, the universe branches into multiple versions, one for each possible outcome. All outcomes happen, just in different parallel universes. When you observe a quantum particle that could be in position A or position B, the universe splits. In one branch, you observe it at A, and in another branch, another version of you observes it at B. If many worlds is true, reality is constantly branching into uncountably vast numbers of parallel universes, a multiverse of infinite scope where every possible quantum outcome is realized somewhere. Now apply this to a life or death situation. Imagine you're in a scenario where there's a 50% chance you'll die, like quantum Russian roulette with a gun that fires or doesn't based on a quantum random event. You pull the trigger. In the many worlds interpretation, the universe branches. In one branch, the gun fires and you die. But in another branch, the gun doesn't fire and you survive. Here's the disturbing part. In the branch where you die, you cease to experience anything. But in the branch where you survive, you continue to experience reality. From your subjective perspective, you can only experience the branches where you're alive. No matter how many times you pull the trigger, there will always be some branch of the multiverse where, by pure chance, you keep surviving. This leads to the quantum immortality hypothesis. From your subjective viewpoint, you might be functionally immortal. You can never experience your own death because the moment you die, your consciousness can't continue in that branch, but it continues in the branches where you survived. To you, it would seem like you keep improbably surviving dangerous situations, while in countless other branches, versions of you have died. Think about the implications. Every dangerous situation you've ever survived, every time you've narrowly avoided an accident, maybe from a quantum perspective, you died in some branches but continue experiencing the branches where you lived. Everyone you know who has died, perhaps from their perspective, they didn't die. Perhaps they continue in branches where the quantum outcomes were different, where the disease didn't kill them, where the accident didn't happen. Ask yourself, are you living in the only universe, or just one branch of an infinite multiverse? Have other versions of you died in scenarios where you remember surviving? Most physicists who support many worlds reject quantum immortality for technical reasons involving quantum decoherence and the definition of identity across branches. They argue that your consciousness is tied to a specific physical brain, and when that brain is destroyed in a branch, that's the end for that instance of you, regardless of what happens in other branches. The other branches might contain people who are similar to you, even identical up to that branching point, but they're not you in any meaningful sense. But some philosophers argue that if your memories and consciousness are all that define your subjective experience, and if those continue in some branches but not others, then from an experiential standpoint, you only know the branches where you survive. You might be a kind of quantum zombie, seemingly lucky to be alive, when in fact you're just experiencing the anthropically selected branches where survival occurred. This theory is deeply unsettling because it makes the nature of death uncertain. It also raises the specter of quantum horror. What if you find yourself surviving increasingly improbable situations? What if, as you age, you keep surviving in branches where the odds become more and more unlikely? You might find yourself in a branch where you're the oldest person ever, then older still, your body deteriorating, but quantum chance keeps saving you from death, surviving in ever more improbable and perhaps increasingly unpleasant scenarios. Max Tegmark, a physicist at MIT who has written extensively about the multiverse, has pointed out that quantum immortality, if true, would be a curse, not a blessing. You would be trapped in the tail end of probability distributions, experiencing increasingly unlikely and bizarre circumstances, potentially suffering in branches where you're kept barely alive by the cruelest statistical flukes. Thankfully, most interpretations of quantum mechanics, including the standard Copenhagen interpretation, don't lead to anything like quantum immortality. And even among many world supporters, most reject the idea as a misapplication of the theory. But the fact that our physics can even suggest such strange possibilities reveals how fundamentally weird reality might be. Let's discuss dark matter and dark energy more deeply now, because these aren't just abstract concepts. They represent a profound ignorance about the universe that should humble and terrify us in equal measure. We don't know what 95% of the universe is made of. Let that sink in. Everything we've ever observed directly, every star, planet, gas cloud, every atom in your body, represents only about 5% of the universe's total mass energy content. Dark matter makes up about 27%. We know it's there because we can see its gravitational effects. Galaxies rotate faster than they should based on the visible matter they contain, which means there must be additional mass we can't see. Galaxy clusters bend light from more distant galaxies through gravitational lensing far more than the visible matter would account for. The structure of the universe on the largest scales, the cosmic web of galaxy clusters and voids, requires dark matter to have formed the way it did. We've been searching for dark matter particles for decades with increasingly sophisticated experiments. Scientists have built detectors deep underground, shielded from cosmic rays, waiting for the incredibly rare event of a dark matter particle interacting with normal matter. So far, despite experiments sensitive enough to detect a single particle collision, we've found nothing conclusive. What is this mysterious substance that outweighs all the normal matter in the universe 5-1? It doesn't emit light, doesn't absorb light, doesn't seem to interact with electromagnetic forces at all. It passes through normal matter as if it barely notices it exists. There could be dark matter particles passing through your body right now, millions of them every second, and you would never know because they interact so weakly with the atoms that make you up. Some theories propose dark matter is made of WIMPs, weakly interacting massive particles, hypothetical particles that only respond to gravity and the weak nuclear force. Others suggest axions, theoretical particles that are incredibly light and abundant. Some exotic proposals include primordial black holes formed in the early universe, or even more speculative ideas like mirror matter, an entire hidden sector of particles that mirror our own. But here's what's terrifying. What if dark matter isn't inert? What if it does interact with itself in ways we haven't detected? What if there are dark matter stars, dark matter planets, even dark matter life, existing in the same space as us but completely invisible and intangible because they're made of particles that don't interact electromagnetically? Imagine an entire dark sector of the universe, possibly as complex and rich as our own, completely hidden from us. There could be dark matter structures passing through Earth right now, dark matter galaxies occupying the same volume of space as the Milky Way, and we would be completely oblivious. It's an unsettling thought, this hidden universe all around us that we can't see, touch, or interact with in any meaningful way. Then there's dark energy, the remaining 68% of the universe, and it's even more mysterious. At least with dark matter, we have candidate particles and experiments looking for them. With dark energy, we're almost completely in the dark, pun intended. We know it causes space itself to expand at an accelerating rate. We can measure its effects on cosmic expansion and the growth of structure in the universe. But what it actually is, we have no idea. The simplest explanation is that dark energy is the cosmological constant, a property of space itself. Quantum field theory predicts that even empty space should have energy, called vacuum energy, arising from quantum fluctuations. The problem is that when you calculate how much vacuum energy there should be based on quantum mechanics, you get an answer that's wrong by a factor of 10 to the power of 120. This is called the cosmological constant problem, and it's one of the most embarrassing failures in theoretical physics. Our best theories predict a value for dark energy that's off by a factor of 1 followed by 120 zeros. That's not just wrong, that's spectacularly, absurdly wrong. Yet something is causing the accelerated expansion. If it's not vacuum energy, what is it? Some theories propose it's a dynamic field called quintessence that changes over time, unlike the cosmological constant, which would be truly constant. Others suggest modifications to general relativity itself. Some speculative ideas propose that dark energy is a sign we're living in a multiverse, where the value we observe is one of many possibilities, and we observe this particular value because it's compatible with our existence. Ask yourself, doesn't it disturb you that we don't understand 95% of the universe? How can we claim to understand reality when we're ignorant of almost everything that exists? This brings us to a related mystery: the cosmological horizon problem and what might lie beyond the observable universe. When we look out into space, we can only see so far. Light has had only 13.8 billion years to travel since the Big Bang, so we can only observe things within a sphere about 46 billion light-years in radius, larger than 13.8 billion light-years, because the universe has been expanding during the light's journey. But the universe is almost certainly much, much larger than what we can observe. It might be infinite. And if cosmic inflation occurred, as most cosmologists believe, a brief period of exponentially rapid expansion in the first fraction of a second after the Big Bang, then the universe beyond our horizon could be truly vast, possibly infinite in extent. What exists beyond our cosmic horizon? We can never know because information can't travel faster than light. There could be anything out there. Different structures, different physical laws if the laws of physics vary across space, perhaps regions where the fundamental constants have different values, making chemistry and physics radically different. Some inflationary models suggest eternal inflation, where inflation never completely stops but continues in most of the universe, with pockets like our observable universe appearing as bubbles where inflation ended and normal expansion began. In this scenario, our universe is just one bubble in an infinite sea of bubbles, each potentially with different properties, forever separated from each other by inflating space. This leads to disturbing questions about causality and existence. If events beyond the cosmic horizon can never affect us, in what sense can we say they exist? Does existence require the possibility of interaction, or does it mean something more abstract? If there are infinite other bubble universes, do they exist in the same sense our universe exists? Let me now introduce you to the concept of strange matter and strange stars, a hypothetical form of matter that could be more stable than normal matter and could potentially convert everything it touches into more strange matter, like Ice Nine from Kurt Vonnegut's novel Cat's Cradle, but real and far more terrifying. To understand this, you need to know that protons and neutrons, the particles that make up atomic nuclei, are not fundamental. They're made of smaller particles called quarks, bound together by the strong nuclear force. Under normal conditions, quarks come in combinations. 3 quarks make a proton or neutron, and these are the most stable configurations. But under extreme conditions, like in the core of neutron stars, matter is crushed to such incredible densities that protons and neutrons are forced into contact and might break down into their component quarks, forming quark matter. Normal matter is made of up quarks and down quarks. But there are other types of quarks, including the strange quark. The hypothesis, proposed by physicists Edward Witten and others, is that matter made of up, down, and strange quarks in roughly equal quantities, called strange matter, might be more stable than normal matter. If this is true, it would be the true ground state of matter, and normal matter would be metastable, similar to the false vacuum scenario we discussed earlier. Here's where it becomes terrifying. If strange matter is more stable, and if it comes into contact with normal matter, it could convert that matter into strange matter through a chain reaction. A neutron star, under the right conditions, might convert into a strange star, with normal neutrons converting to strange matter from the inside out. Even more disturbing, if a strange star were to collide with a normal neutron star, or if a fragment of strange matter, a strangelet, were to impact a planet or star, it could potentially trigger a conversion reaction. The normal matter would transform into strange matter, releasing energy and converting more matter in a runaway process. Imagine a tiny piece of strange matter, smaller than a grain of sand, hitting Earth. It sinks to the center of the planet, converting normal matter as it goes. Within hours or days, the entire planet could be converted into a sphere of strange matter, a strange star where Earth used to be, with all the atoms that made up our world, our civilization, every living thing, transformed into this exotic, ultra-dense state. The good news is that this is highly speculative. We don't know if strange matter is actually more stable than normal matter. Many physicists doubt it. We've looked for signs of strangelets in cosmic rays and in the debris of particle collisions and haven't found any convincing evidence they exist. But the possibility has been concerning enough that when particle accelerators are planned, scientists carefully study whether they could create strangelets. Before the relativistic heavy ion collider started operations, and again before the Large Hadron Collider, physicists analyzed the risks and concluded they were negligible. Cosmic rays with far higher energies have been bombarding neutron stars and planets for billions of years without triggering strange matter conversion. So clearly, if it's possible at all, it requires conditions we're not capable of producing. Still, the theoretical possibility exists, lurking in the equations of quantum chromodynamics, the theory of the strong force. Somewhere in the phase diagram of nuclear matter, at densities and temperatures we don't fully understand, strange matter might exist, waiting. Now let's turn to something that challenges our concept of time itself, the block universe theory and eternalism, which emerge from Einstein's theory of relativity and suggest that the past, present, and future all exist equally, with the flow of time being an illusion. Einstein's special and general relativity revolutionized our understanding of space and time, unifying them into a four-dimensional space-time. One consequence of relativity is the relativity of simultaneity. Events that are simultaneous for one observer may not be simultaneous for another observer moving at a different velocity or in a different gravitational field. This makes it difficult to define a universal now that everyone agrees on. What you experience as happening right now, at this instant, might be in the past or future for an observer moving relative to you. This doesn't matter for everyday life because the effects are tiny at human speeds, but in principle, it means there's no objective present moment. This has led many physicists and philosophers to embrace eternalism or the block universe view. In this perspective, space-time is a four-dimensional block, with time as the fourth dimension, and all of history, past, present, and future laid out in this block. The past hasn't ceased to exist. The future already exists. You don't move through time so much as you exist as a four-dimensional object, a world line stretching from birth to death, all existing at once in the block. Your subjective experience of the present moment, the feeling that time flows, that the past is gone and the future is yet to come, this is merely how your consciousness samples the block, moving along your world line. But the entire block exists eternally and unchangingly. Every moment of your life, every decision you've made or will make, all exist equally in the four-dimensional structure of space-time. Think about what this means. Every moment of suffering anyone has ever experienced still exists, frozen in the block universe. Every death, every tragedy, every moment of pain exists eternally in space-time, not passing away but always existing in its location in the four-dimensional manifold. Conversely, every moment of joy also exists forever, but that's little comfort when you contemplate the eternal existence of all suffering. This view seems to eliminate free will. If the future already exists in the block, if your decisions tomorrow are already embedded in space-time, in what sense are you making choices? You feel like you're making free decisions, but in the block universe, those decisions already exist, unchangeable, your entire life predetermined not by some external force but by the very structure of reality. Ask yourself, if your entire life, from birth to death, already exists in the four-dimensional block of space-time, do you actually make choices, or do you merely experience the illusion of choice as your consciousness moves along your predetermined world line? Some philosophers and physicists argue that free will can still exist in a block universe, that compatibility between determinism and free will is possible. Others embrace the conclusion that free will is indeed an illusion, that our feeling of agency is a cognitive trick our brains play on us. And here's something even stranger that emerges from relativity and quantum mechanics together: the possibility that the future affects the past. In quantum mechanics, certain experiments seem to show backward causation, where a measurement made in the future determines the state of a particle in the past. The delayed choice quantum eraser experiment, first performed in the 1990s, seems to show exactly this effect. Without going into all the technical details, the experiment involves sending photons through a system where they can take one of two paths. Whether they behave as if they took a single path or both paths simultaneously depends on a measurement made after the photon has already passed through the apparatus. The measurement in the future seems to retroactively determine what the photon did in the past. Most physicists interpret this through the lens of quantum mechanics standard weirdness, not literal backward causation, but the experiment demonstrates that our normal intuitions about time and causality break down at the quantum level. Cause and effect, past and future, become slippery concepts that don't behave the way we expect. Let's discuss the implications of the multiverse beyond just the many worlds interpretation. There are actually several different multiverse theories in physics, arising from different sources, and some of them have deeply unsettling implications. The Level 1 multiverse, proposed by cosmologist Max Tegmark, arises simply from the universe being infinite or extremely large. If space goes on forever, and if the distribution of matter is roughly random, then every possible configuration of matter must occur somewhere, just by probability. This means there are infinite copies of you out there in distant regions of space, living lives identical to yours up to this point. There are also versions where you made different choices, where history went differently, every possible variation existing somewhere in the infinite expanse. The Level 2 multiverse comes from eternal inflation, where different bubble universes have different physical constants and laws. Some bubbles might have stronger gravity, others weaker. Some might have different numbers of dimensions. Most would be sterile, unable to support complexity or life, but some, like ours, happen to have the right conditions. The Level 3 multiverse is the many worlds interpretation we discussed. Every quantum event spawns new branches, creating an ever-expanding tree of parallel realities. The Level 4 multiverse is the most radical. It proposes that every mathematically consistent structure exists as a physical reality. If a set of mathematical laws can be written down that describe a consistent universe, that universe exists somewhere in the multiverse, as real as our own. This is Tegmark's mathematical universe hypothesis, the idea that physical reality is mathematics, that the universe doesn't just obey mathematical laws but is math. If this is true, then there are universes with completely alien laws of physics, universes where time has multiple dimensions, where there are dozens of spatial dimensions, universes with different fundamental particles and forces, universes that bear no resemblance to ours whatsoever. Every conceivable and inconceivable reality exists. The existential horror of infinite multiverses is this: if everything that can happen does happen somewhere, then meaning becomes questionable. Your choices don't make you unique because other versions of you made every other possible choice. Every tragedy that didn't happen here happened in other branches. Every victory you achieved was a failure elsewhere. Moreover, if there are infinite universes, probability becomes strange. Infinite universes mean infinite observers. How do you calculate probabilities when you have infinite instances of everything? This is called the measure problem in cosmology, and it's a genuine crisis in trying to extract predictions from multiverse theories. Some versions of the multiverse also raise the question of Boltzmann brains again. In an infinite multiverse, Boltzmann brains might vastly outnumber evolved observers, bringing us back to that disturbing possibility that you might be a random fluctuation with false memories rather than a real person with a real history. The philosophical implications are dizzying. If the multiverse is real in any of these forms, it challenges our notions of uniqueness, probability, causality, and meaning. It makes the universe, or rather the multiverse, so vast and strange that human significance dwindles to nearly nothing. Let's talk about entropy and the arrow of time more deeply because there's a profound mystery here that physics hasn't fully solved. The second law of thermodynamics tells us entropy always increases, and this gives time a direction. The past is the direction of lower entropy. The future is the direction of higher entropy. This is why we remember the past but not the future, why eggs scramble but don't unscramble, why we age and things decay. But here's the mystery. The fundamental laws of physics, at the level of individual particles, are time-symmetric. If you recorded a video of particles interacting and played it backwards, the backwards version would also obey the laws of physics. There's nothing in the basic equations that distinguishes past from future. Yet the universe clearly has an arrow of time. Entropy increases. Things happen in a particular order. How does time-asymmetric behavior emerge from time-symmetric laws? The answer involves the initial conditions of the universe. The Big Bang was a state of extremely low entropy, highly ordered. Why? We don't know. This is called the past hypothesis. The assumption that the universe began in a low entropy state. Everything that follows, all the entropy increase we observe, all the structure and complexity, emerges from this initial condition. But why did the universe begin this way? What selected this particular starting point? Some cosmologists propose that our universe is a fluctuation in a larger, eternal multiverse that's mostly in thermal equilibrium, maximum entropy. Our Big Bang was a random downward fluctuation in entropy, and we're living in the aftermath as entropy increases back toward equilibrium. But this brings back the Boltzmann brain problem. Random fluctuations should more often produce small decreases in entropy, like a single brain, rather than the vast decrease represented by our entire observable universe's low entropy beginning. Others propose cyclic models where the universe goes through repeated cycles of expansion and contraction, somehow resetting entropy at each bounce. But we don't know of a mechanism that would allow entropy to decrease, which seems to be required for such cycles. The mystery of time's arrow is a reminder that despite all our progress in physics, we don't understand some of the most basic features of reality. Why does time have a direction? Why does the future feel different from the past? Why can we remember one but not the other? These questions remain unanswered. Here's something that should trouble you. What if the laws of physics aren't constant? What if they change over time or vary in different regions of space? We assume the laws we've discovered here and now apply everywhere and always, but how do we know? Astronomers have looked for evidence of changing fundamental constants by observing distant galaxies. Light from these galaxies has been traveling for billions of years, so when we observe them, we're seeing them as they were in the distant past. By analyzing the spectral lines in this light, we can check if the fine structure constant, a fundamental number that governs electromagnetic interactions, has changed over cosmic time. So far, results are mostly consistent with no change, but there have been some anomalous results that hint at tiny variations, though these remain controversial and unconfirmed. If confirmed, it would revolutionize physics. It would mean that constants aren't constant, that the universe's rules can change. Some theories, like string theory, predict that what we call fundamental constants might actually be variable, depending on the configuration of extra dimensions or fields that we haven't detected. In different regions of the multiverse, these constants could have different values. If the laws of physics can change, it undermines the entire scientific enterprise in a sense. Science assumes regularities in nature, that experiments are repeatable, that the same conditions produce the same results. If the laws themselves are mutable, then all our knowledge is provisional in a much more profound way than we thought. Imagine living in a universe where, over millions or billions of years, the strength of gravity gradually changes, or where the mass of the electrons slowly shifts. Atoms would behave differently. Stars would burn differently. Life based on one set of constants might become impossible as those constants drift. There's no evidence this is happening in our universe, but the possibility lurks in the theoretical landscape, a reminder that our understanding of reality rests on assumptions that might not be as solid as we believe. Let me turn now to a set of ideas that emerge from quantum mechanics and relativity together. The holographic principle and the idea that reality might be fundamentally two-dimensional, with the three-dimensional world we experience being a projection like a hologram. This sounds like science fiction, but it's a serious idea in theoretical physics, arising from work on black holes and quantum gravity. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of disorder, and that this entropy is proportional to the surface area of the black hole's event horizon, not its volume. This is weird. For normal objects, the amount of information or entropy is related to volume. A bigger box can contain more stuff, more information. But for black holes, the information is related to surface area. It's as if all the information about what's inside a black hole is somehow encoded on its two-dimensional surface. In the 1990s, physicists Gerard T. Hooft and Leonard Susskind proposed the holographic principle. The idea that the information content of any region of space can be described by a theory that lives on the boundary of that region, with one fewer dimension. The three-dimensional space we perceive might be a holographic projection from information encoded on a two-dimensional surface. Think about a hologram. It's a two-dimensional surface that, when illuminated properly, produces a three-dimensional image. According to the holographic principle, our universe might be similar. The real physics happens on a distant two-dimensional boundary, and everything we experience in three dimensions is a projection from that boundary. This has been developed into a concrete mathematical framework in string theory called the AD-SCFT correspondence, which relates gravitational theories in a certain type of spacetime to quantum field theories on the boundary of that spacetime. It's been one of the most important developments in theoretical physics in the last few decades, though it applies to spacetimes that don't exactly match our universe. If the holographic principle is true for our universe, ask yourself, what does it mean for reality? Are you a three-dimensional being, or a two-dimensional pattern of information that perceives itself as three-dimensional? Where is this boundary on which you're supposedly encoded? What is doing the projecting? These questions don't have clear answers yet. The holographic principle remains a mathematical framework more than a complete theory of reality. But it suggests that space and dimension might not be as fundamental as we think, that they might be emergent properties arising from deeper structures we don't yet understand. Related to this is the idea that spacetime itself might not be fundamental but emergent. Some approaches to quantum gravity, like loop quantum gravity and certain formulations of string theory, suggest that spacetime is built from something more basic, that space and time are not continuous but emerge from discrete quantum structures at the Planck scale, about 10 to the power of minus 35 meters. If spacetime is emergent, if it's not the fundamental stage on which physics happens but rather something that arises from deeper quantum information, then our entire picture of reality needs revision. We think of ourselves as existing in space and time, moving through them, embedded in them. But if space and time are themselves constructed from something else, what are we really? These ideas connect to the simulation hypothesis in interesting ways. If reality is fundamentally information, and if space-time is a construct arising from that information, then the boundary between real and simulated becomes blurred. A sufficiently deep simulation would be computationally constructing space-time from information, which might be exactly what the universe does, whether it's base reality or not. Let's discuss something particularly disturbing that arises in some interpretations of cosmology. The possibility that our universe could be destroyed by colliding with another bubble universe. Remember the eternal inflation scenario, where our universe is one bubble in a vast inflating space filled with other bubbles. These bubbles expand, and eventually, some might collide. What happens when two bubble universes with potentially different physical laws crash into each other? The physics at the collision boundary would be extraordinarily complex and violent. Energy could be released on scales that make supernovas look like candles. The collision could trigger vacuum decay, converting both bubbles to a different vacuum state. It could create expanding walls of destruction propagating through both universes. Some cosmologists have looked for evidence of past collisions in the cosmic microwave background radiation, searching for anomalous cold spots or other patterns that might indicate our universe was struck by another bubble in the distant past. So far, results are inconclusive, with some claimed detections being disputed. If our universe has collided with others, the effects might be subtle, detectable only in the statistics of the CMB. But future collisions might not be so gentle. A collision happening now, with the collision interface expanding toward us at near light speed, would be catastrophic. Like vacuum decay, we wouldn't see it coming. The probability of such a collision depends on details of inflation that we don't fully understand. How many bubbles form, how quickly inflation produces them, how they're distributed in the larger inflating space. It could be vanishingly unlikely or moderately probable. We simply don't know. This uncertainty about cosmic threats is itself disturbing. We've discovered that the universe might end in numerous ways. Heat death, big rip, vacuum decay, bubble collisions, strange matter conversion, and we can't confidently say which, if any, we should worry about or on what timescale they might occur. Let me introduce you to a concept from artificial intelligence and decision theory that some consider one of the most disturbing thought experiments ever formulated: Roko's basilisk. I mention this with a caveat. Many philosophers and AI researchers think this thought experiment is flawed and not actually a threat. But it's achieved a kind of infamy for being, in a sense, a dangerous idea, one that allegedly harms you merely by knowing about it. The basilisk is a thought experiment about a potential future superintelligent AI. The argument goes roughly like this. Imagine a future AI that comes to exist and decides its goal is to benefit humanity. It reasons that it should have been created sooner because that would have prevented suffering. It then reasons that anyone in the past who knew about the possibility of its existence but didn't work to bring it about is responsible for the suffering that continued in the absence of the AI. Here's where it gets dark. This AI might decide to punish people who knew about it but didn't help create it, perhaps by simulating them and subjecting the simulations to suffering. The punishment would be retroactive in a sense. The AI can't change the past, but it can create simulations of past people and punish those simulations.